Hey folks, thanks for watching my video. You can watch it any speed you want. Remember, you just go down, adjust the little gear, run it at 1.5 speed, 2 times speed, whatever. But I do want you to get through the whole video because there's pieces of information I want you to pick up, not just at the beginning, but middle and end of the video. Thanks. So here's what we're doing today. We're going to try to solve a system of equations. What is that? We're looking at a set of two or more equations. Today, there's just going to be two equations. And the equations will have the same variables like x and y. In reality, like in higher level math, they can have, you know, 10 different variables. And you're solving a system as an engineer or a scientist trying to find a solution to a problem. And right now we're kind of beginners at this. Well, you might not feel that way. You might say, well, we've done this in algebra 1 or integrated 1 or whatever. Did this in 7th grade. I know. We're going to try to graph the lines though today by hand. Okay. And so we're going to try to practice our graphing skills. And so let's talk about that. This would be a situation where you have one solution, right? Because we're looking for where the two lines intersect. What point do they have in common? And so if they intersect, then they're consistent. Okay, so let's put that down right now. That means there is at least one solution. Okay, so if they intersect, then there's a solution. Okay, and that's what we're looking for. We're looking for the solution. If they don't intersect, then there's no solution. Okay, so no solution if they don't intersect. So obviously this one right over here, there are two lines that are parallel to each other. This is an inconsistent situation, inconsistent. And this one right here, well, these two are both consistent. You might say, well, I only see one line over here. We're going to talk about that in just a second. Okay, so hold your horses. So what if they intersected? What would our situation, what would our equations look like? Well, like you can see the y-intercept right here is positive. So I'm going to make up a number for the y-intercept. I'm going to say it's like 3, okay? And then the slope might be 1, like we're going up 1 over 1, up 1 over 1. So I'm going to emphasize the slope being 1x plus 3. So if the slope is 1 and the y-intercept is 3, our line might look like that, right? Now, let's look at this line. The y-intercept is negative, and I'm just eyeballing this, but it looks like it's about 3 times further down. So I'm going to say that second line has a -9 slope, or -9 y-intercept. Sorry about that. And the slope looks like it's like up twice as much as it is over. So I'm going to call the slope 2x. All right. So if you saw something like this where their slopes are different, then the lines are going to intersect at one point. Okay. If the slopes are different. Now, here's a tricky situation. You might only see one line here, but that could be two different equations. Well, the same equation that just looks completely different. So let me explain, okay? So this line almost looks the same as that one that we had over here. So I'm going to put down y equals 2x, doggone it, it was y equals 1x plus 3, okay? And then let's say we multiply each one of the variables here by 2. So this becomes 2y equals 2x plus 6. So the two equations, they look a little different, but if you study them closely, this one here through division by 2 could be transformed back into this equation here. So really they're the same exact equation. They just look different. Guys, look, because I generated this second equation from the first equation, you're probably going, well, duh, Nelson, I can see that. It's not always going to be that obvious. They could have two equations down, and you can't really see immediately that they're the same equation. So you're going to want to reduce them down to the same format. Like this one, I can see I could divide each one of them by 2. So if I did that work, divide this by 2, this by 2, this by 2, I would get y equals 1x plus 3. As soon as I see that the two equations are identical to each other, I probably wouldn't even graph them. I would say, look, they are consistent. Now, here's another set of vocab that we need to understand. There are these words independent and dependent. Okay, dependent. So if you have a consistent solution, you have at least one answer, then they can be broken down into these two words. Independent means you have one solution, and dependent means you have infinitely many solutions. I'm going to put that infinite sign down so I don't have to spell the word out. Infinitely many solutions. Now, how can infinitely many solutions happen? Well, the two lines are really just sitting on top of each other. Okay, so that's what they use the word dependent for. So I'm going to put that word. Oh, let's put it over here in red. This is a dependent situation, dependent, and this one is independent over here. And when we look at this third one, it doesn't get the words independent or dependent because it's inconsistent. It doesn't have a solution. So this one has no solution, and so it doesn't get those special words of independent or dependent. All right. So I hope I'm making this clear. Oh, let's put down one last thing here. How could this, how could this situation exist? Well, you'd have the equation like y equals, let's say this y-intercept is like 10 up here. Okay. So I'd have like y equals 1x plus 10. And then let's say this one is like -2 right down here for y-intercept. So I'd have y equals 1x minus 2. So if their slopes are the same, here we've got, a slope of 1, right? If their slopes are equal to each other, then we have a inconsistent solution or two parallel lines, okay? Two parallel lines. All right, so I'm going to do another video with some examples. These were just the notes that I wanted you to put down today. Thanks for watching my video.